Today we will start the pressure measurement. Pressure is another important variable in process industries, chemical and process industries. We have already learnt the other temperature measurement. Next is pressure measurement. This pressure is liquid pressure, liquid or gas pressure measurement. In machine design, we have another pressure that is called contact pressure. When two solids sits one over the other, two solids, then the surface pressure is there between the two solids, that is called Hertz pressure, and that is a different aspect. So here we are going to see gas, and that is fluid pressures. When a fluid is contained in a vessel, it exerts equal pressure in all directions. So that is the pressure what we are going to measure. Unit for pressure is Pascal. Unit is Pascal. That is equal to 1 Newton per meter square. That is the unit for pressure. And we have the 1 bar. This also used as unit for pressure. That is equal to 10 to the power of 5 Pascal. 1 bar is equal to 10 to the power of 5 Pascal. And 1 atmospheric pressure is nearly about 1 bar. Strictly speaking, 1.01 bar is equal to 1 atmosphere pressure. So we will say 10 to the power of 5 Pascal is equal to around 1 atmospheric pressures. That is 1 kilogram force per centimeter square. Also, people call it as atmospheric pressure. So these are the basic units. Now the unit normally used for calibration of pressure gauges is dead weight pressure gauge. The principle of functioning is like this: there is a plunger and cylinder and a respirating pump to develop pressure in the liquid, and the gauge to be calibrated is fixed here, and we can by rotating this piston we can move the piston forward or backward, and thereby developing the pressure in the or releasing the pressure in the liquid in the setup. And fine adjustment, we can use this bleed valve to take away little liquid so that fine adjustment also can be made. So when there is no pressure developed, the plunger will sit at the bottom, and when you rotate this, the pressure builds up, and when the pressure into this plunger area is equal to the dead weight of the, now this is dead weight from this, before adding this calibrated disc only dead weight alone will be there. So by rotating we can make this float when the pressure developed in the liquid into the area of the plunger is equal to the weight of this plunger, then it starts floating. And some pressure value might have written, it's calibrated piston plunger, and whatever the pressure shown is same pressure indicated by the instrument as well as the true pressure in the liquid, which is written here on the plunger, can be noted down. So we can conduct this calibration, that is true pressure PR and indicated pressure PI. So this is serial number. So like that, whatever we have learnt under static calibration, we can develop different pressures here by adding more and more calibrated disc. Each disc you will have some pressure is written. 4 or 5 discs means add those pressures together. That is the total pressure developed, and whatever indicated they are written here, true pressure and the indicated pressure in the instrument, and a set of readings can be taken, and again from the high pressure we can again go back to the low pressure. So that is the way we have learned the static calibration. It can be done here. So the pressure developed in this liquid is measured by balancing with the calibrated disc, and that is used for calibration purpose. The error source here is the friction, static friction between the cylinder surface and the piston, and that can be made as small as possible. When we take measurement, just twist this piston plunger, then as it rotates, then you find the static friction is removed, and only dynamic friction will be there, which will be very small one. So that can be taken care of while we take measurements. And next principle is manometer. Manometer is well known. So we have a this is a YouTube manometer. Yeah, YouTube manometer. It is in this form. So we mostly used for measuring differential pressure. Also we can measure the atmospheric pressure by barometer, that is having vacuum at one end, the other end the atmospheric pressure acts, that is barometer. It is an inversion of the, or one of the modifications of manometer. So barometer, inclined manometer, and micro manometer, Sisson or well type manometer. These are all different types of manometers. So essentially it measures the pressure difference P1 minus P2 is equal to say mostly the liquid used in manometer is mercury. So the P1 minus P2 is equal to specific weight of mercury into difference in the height. Here you will have a scale with which you can take reading between this level and that level, and that decides the P1 minus P2. So detail of this can be obtained anywhere in the literature. So we will go to the other types which are mainly used in measurement in medium and low pressures and high pressures, what are often used here. They can be classified under these three groups: pressure measurement, Bourdon tubes, diaphragm types, and bellows. These are the three elastic elements. These are useful for elastic, made up of say phosphor bronze, beryllium copper, stainless steel. These are the material used to make the elastic pressure transducers. And the Bourdon tube, which we have seen in one of the introductory classes, is of three types. One is C type, helical type, and spiral type. And we can measure up to 7,000 bar by these any one of these Bourdon tubes. We can measure up to 7,000 bar. The principle is if you take the cross section, it is oval cross section. This is the material, and the liquid pressure will be allowed inside. So it is allowed inside, it will occupy. So as the pressure increase, this will assume more or less a circular cross section. In the process, this free end makes a motion. So that free end motion is taken by linkages and given to a rack and pinion mechanism. This lever mechanism pivoted here. So the pinion axis is given to a pointer which moves over a scale, calibrated scale. So for higher pressures, the thickness is increased. To measure higher pressure, thickness is increased, and also it is more and more it will near circular cross section. Very high pressures, the ovality is small for Bourdon tubes for measuring high pressures. So when ovality is reduced, then the amount of deflection is reduced. To compensate for this, people go for helical or spiral type of Bourdon tubes. That is, the pressure is allowed here. It is this is the Bourdon tube in helical form. This is the free end, fixed end, closed end, and when pressure is there, this end will make motions in this direction. So this also used at very high pressures. Similarly, in spiral type, here pressure is allowed, and it is allowed the closed end of the spiral is here. So this end makes to and fro motions. So like this, whatever we have shown, you can have linkage mechanism for reading static pressures. If you want to have, if there is any dynamic pressure, probably we can connect a wiper and convert this wiper motion into electrical signal. Using potentiometer transducer, you can convert into electrical signal, and then we can process it. That's also possible in this type also. It's left to us. If we convert this motion into electrical quantity, we can use it also for slowly varying dynamic signals, pressure variations. But in dynamic pressures, the tube carrying the dynamic pressure, we should be careful, because when a pressure fluid flows through any small piping, that frequency is damped out. So we should have, whenever we carry dynamic pressures to an instrument, we should have sufficiently large cross section, so the pressure variation truthfully transmitted to the instrument end. This we have to be careful. Otherwise, whatever the dynamic pressure taking place in this vessel cannot be carried by a thin tubing to an instrument, or we have to mount the instrument itself on the tank itself or pressure vessel wherever we want to measure. That precautions we have to take. So next one is diaphragm. Diaphragm, we have got two types: flat diaphragm and corrugated diaphragm. Flat diaphragm is just a thin sheet, again made up of spring material, fixed at the rim. And when you apply pressure on one side, you find it is deforming. Yeah, it deforms like this, and that means the pressure is converted into force according to this signal flow diagram. This is pressure. When we apply it over an area, it converts into force. Pressure times the area of the diaphragm. that force is deforming the diaphragm material. So stress and strain are induced. What are the types of strain induced? You can find this radial stress and tangential stress accordingly. Strain also radial and tangential strains will be induced. If we find near the fixed end of the diaphragm, we have got compressive stress or strain. Both radial and as well as tangential directions, we have compressive strain. And near about the middle of the diaphragm, we have the tensile strain. So accordingly, fix the strain gauges. 1, 3 will pick up the compressive strains. 2 and 4 will pick up the tensile strain. So this is 1, 2, 3, 4. 1 and 3 compressive, 2 and 4 tensile. So this gives the maximum sensitivity for the bridge network. So the epsilon strain produced is picked up by the strain gauge, and R is changed. Yeah. So resistance of the strain gauge is changed. Then we find we get an output from the bridge network. If it is this is a DC excitation, so we can use a DC amplifier, and we get the output voltage XO. This is DC amplifier. Or we can also use a AC excitation for this by using a carrier frequency amplifier, which you have learnt already. Yeah, that is the next type is corrugated diaphragms. The disadvantage of the flat diaphragm is the maximum deformation of a flat diaphragm can be 1/3 the thickness of the diaphragm. So this is one diaphragm where T is the thickness of the diaphragm. 1/3 the thickness alone it can deform. More than that, the deformation is non-linear to pressure applied. So to overcome this drawback, people go for the corrugated diaphragm. Corrugated diaphragm is somewhat like this. This is C-type, which we have seen already in one of the earlier classes. This is a board-on tube. It's a C-type. It's a C-type board-on tube, what we have seen just earlier. And in place of it, we go for helical or the spiral, depending upon the pressure range. So that is the board-on tube, and this is a corrugated diaphragm. This is a corrugated diaphragm. You have the wavy nature in the surface of the diaphragm. Flat diaphragm means it will be flat area. Here you have got the waviness on the surface, and this gives rise to much more deformation than what is normally available in the flat diaphragm. I will show the other one also, which will come later, bellows. This is the called bellows. We find the so-called convolutions. So everything is made up of spring material. But here that is what is bellow is shown there, which you will see little later. So it is the convolutions are produced, and the two ends are open, as it is shown. The two ends are open here. We have to plug it if you want to use it, but what is available in the market, it is of this type. So you have to plug one side with turning a piece and fix it properly. In the other one, we make a small hole so that through which we can apply the pressure. So that you will come little later how the bellows. So just I want to show you how a bellow looks like when we purchase from the market. Yeah. These are the three basic elements: board-on tube and diaphragm and bellows. So restrictions, 1/3 the thickness of the diaphragm alone it can deform, that is overcome here by going for corrugated diaphragm. So you have got more deformations. Such an instrument one is available in aneroid barometer, which is in aeroplane and all flying at different heights. The atmospheric pressure at that level, it acts over. This is made up of, this is called pressure capsule, made up from two such corrugated diaphragms. This is one corrugated diagram, this is another one. Bring both of them together, and say at the end, at the circumference, you solder it or weld it. So it becomes a capsule. And then when you apply a pressure, that the capsule expands. That expansion is given to this rack, which forms part of the top corrugated diaphragm. And then when the rack moves up and down, when pressure varies, the axis of the pinion is connected to a pointer which moves over a scale. The pressure reading actually is written in terms of the height at which the plane is flying. That is one of the uses of this corrugated diaphragm. So this that is yeah. And now we will go back to the flat diaphragm. We have seen how the flat diaphragm deforms, and the deformation is picked up by strain gauges. That is one possibility of sensing the deformation of the flat diaphragm into electrical signal by using resistance. Strain gauge is basically resistance. So we can use the other principle also. We know to convert a displacement or stress or strain, we can use the displacement of any member. We can use resistance or inductance or capacitance. How the inductance capacitance are made use of made use of in sensing the deflection of diaphragm is illustrated in the following diagrams, figures. So here we have got two inductive pickups, self inductance pickup, and this is the diaphragm, and the pressure difference P1 and P2 are allowed to act in this chamber. The P1 is being higher than P2, so the diaphragm will deform in this fashion. So the diaphragm is made up of a magnetic material. So when it moves nearer one of the inductive pickups, it's nothing but inductive coil. So inductance of that will increase. So L1 will increase, L2 will decrease to the same extent the L1 has increased from the original value. So these two L1 and L2 will form adjacent arms of an AC bridge. The other two can be resistant, pure resistances. We know the condition for the balancing of AC bridge. The impedance product of the opposite arms should be same. At the same time, that phase angle of opposite arms, one opposite arm should be equal to the other one. That is well satisfied if you have two more resistances like this, pure resistances. So these are the conventional AC bridge, which is used to convert this deformation into electrical signal EX. The full instrumentation diagram I have given here, but what we have given, what is the basic transducer used, how it forms part of the full instrumentation, it is shown in this signal flow diagram. That is P1 minus P2, by using diaphragm area, the corresponding force is there on the diaphragm, that is F. P1 minus P2 times the area of the diaphragm will be the force. That force again acts on the diaphragm, make a deformation D2, here D, deformation D. So that deformation is changing the inductance of the coil, and that goes into the AC bridge. That AC bridge gives output of E. This forms this more or less this is output signal. This is your carrier frequency amplifier. Yeah, this is the whole thing forms part of carrier frequency amplifier. So which you don't see like this, but this is what is in the detail which you have learnt earlier. So we get the output signal. That is phase sensitivity demodulator, crystal oscillator, from where we get the excitation, and low pass filter, and we get the output signal. So that is how the inductance can made use of to sense the deformation of the diaphragm into electrical signal. Here there is another version where the deflection of the diaphragm is made use of to change the capacitance of two capacitors. This is the diaphragm. So which when acted upon by two pressures P1 and P2, P1 minus P2, so P1 become larger, it deforms like this. So the distance of these two capacitor, C1 is capacitor 1, C2 the other capacitor C2. This is the common plate is diaphragm, and the fixed plate is obtained by having a gold coating on two glass pieces like this. So if and they will be connected they will suitably connected by wires, and you will find you can build a bridge network somewhat like this. This plate and this plate is nothing but our diaphragm. This is our diaphragm. Same diaphragm, same element. So you can have both of them one element, and this gold coating is the fixed diaphragm. This is your gold coating. So and these are the resistances R3 and R4. So it forms the full bridge, and similar excitation if you give. So more or less same pressure difference to force in the diaphragm, and diaphragm again deforms to D, and here you will have capacitance in the inductance side, capacitance, and C will be the inside L, you write C, and all the other things remain same. You get the output signal. So this way the deformation can be sensed by using capacitance principle into voltage also. Another method also adopted, piezoelectric pressure transducers, the quartz crystals. They are normally used in pairs. Yeah, crystals are used in pairs. That is, there is some advantage. The earthing problem or the earthing problem is solved here. Or for example, you find this is crystal 1, this is crystal 2, one pair we are using, and this is the diaphragm over which the pressure is acting. This is diaphragm. Diaphragm. Now the pressure is acting here. So when the pressure, the signal flow diagram here is the diaphragm. So pressure is acting. So diaphragm area we get the force. This force, these crystals, by using crystals, we convert into charge E, charge or voltage we are converting. So when the pressure acts, then force is there, and that is compressing the crystals, piezoelectric crystals. So the crystals can be arranged in a way that top portion of the crystal, or here bottom portion, will develop negative charges, and ground pieces, these are the ground pieces, metal pieces, ground, metal discs. They will collect the charges accordingly. So middle disc will collect the negative charges from both the crystals, and the outer disc will collect the positive charges. So the insulation problem is solved. Crystals are used in pairs to solve the insulation problem. Because this whole frame will be having only positive charge. Negative charge is inside, so already insulated. If you use in pair, otherwise if you use only one crystal, this bottom portion will be negative charge, but top will be positive charge. In between you have to insulate. In the casing itself you have to insulate. That problem is solved if you use in pairs, and correspondingly you have to adjust, you have to stack it so that one plate will be positive. That is, this plate and this plate are connected, and finally you take the positive charge here, this plate through this negative charge. Then we give it to the charge amplifier, where it is amplified and voltage output can be obtained. So that is the point. In piezoelectric pressure transducer you have to use crystal in pairs. So that is regarding the usage of diaphragm in sensing the pressure or measurement of pressure. Next one is bellows. This is another way of this is another elastic element. Here you have deformation more than even corrugated diaphragm. That is advantage, because we have so many convolutions here, and we allow the pressure here. The pressure acts over this area, end pressure. That is, as I told, that the end of the bellow should be closed with a plug. So the whole area is used to convert this pressure acting into a force. Pressure into area will give force, and that force is this nothing but spring material convolutions that gives way. So by using convolutions, the F is converted into a displacement D. So this D can be made use of to move over a resistance on a potentiometer resistance and convert that displacement into a voltage, corresponding voltage signal. So this is for measuring one pressure. If the outside is atmospheric pressure, we measure the gauge pressure. By having a vacuum surrounding the bellows, we can also measure the absolute pressure. Or we can also use bellows. We can arrange the bellows in a way we can measure the differential pressure also. Two different pressures you can give. Same arrangements you can have here, and here convolutions. You can allow the pressures acting there. This is here if you call P1, and you can allow P2, and connect both of them by a rod. The rod portions, this will move. This D is proportional to P1 minus P2. So bellows can be arranged in different ways to measure absolute pressure or gauge pressure or the differential pressures. If we learn now the vacuum measurement, vacuum is low pressure. Any pressure lower than atmospheric pressure, we call it vacuum. Atmospheric pressure is in another unit 760 millimeter of mercury, or you can call it 760 tar. 1 millimeter of mercury is 1 tar, and that is at temperature 20 degrees centigrade. Whatever the pressure felt at a column of 1 millimeter of mercury, that is equal to 133.3 Pascal, that we call it 1 tar. So the atmospheric pressure we say 760 tar. So anything lower than that we call it vacuum. Vacuum is nowadays very widely used in industries, in manufacture of vacuum flask and television tubes, and braking systems in railways, and in coating of metallic coatings, some glass pieces, and also simulators. In order to simulate the space condition, any chamber has to be evacuated to simulate that vacuum condition in space at a very high at larger heights. So when we create vacuum, naturally we have to measure the vacuum, how much we have created in a chamber. Hence you find the vacuum measurement is also an important parameter. For calibration purposes, people go for this molecular gauge, which can measure up to 10 to the power -4 tar. 10 to the power -4 tar, it can use it, and this is mainly used for calibration because the measurement principle based on the Boyle's law. Yeah, based on the Boyle's law. That's P1 V1 is equal to P2 V2. That is what is made use of here. So it's used for calibration purpose. The principle is like this. Here we have a plunger and cylinder assembly. By withdrawing the cylinder, we can bring down. This is mercury. Mercury is filled up there. By withdrawing the plunger up, moving the plunger up or withdrawing it, we can bring the mercury column in this capillary. These are capillary tubes, and with a bulb, with the spherical bulb connected. So when you withdraw up to this point, now the vacuum pressure can enter into this column, this volume and the capillary tube, it can enter. So the thing is, we have to wait sufficient time until the vacuum pressure uniformly get distributed, because to occupy the full space it takes some time at very low pressures. So wait for some time, 5 minutes or 10 minutes, and then now the measurement process starts. You push down this plunger down. Now the mercury will start rising. The moment it comes here, then from this point onwards up to this, that is entrapped. Further rise, further rise will entrap this vacuum molecules, the gas molecules, and here it will rise, and raise the mercury level by pushing the plunger down until it comes here. This is 0 mark, 0 mark in the scale. Until it comes there, you raise up to here. So this will be mercury. Mercury column is raised until it reaches. At that time, you will find in the other so suppose it is a capillary A, this capillary B. In capillary B, this full volume of V, from here it is given. Manufacturer will give you what is volume. It may come here up to here. The mercury may be occupying the full volume. Now take this height. This is, we call it measurement height. That is what you are supposed to measure after making the mercury column to come to 0 level, and find the height of the compressed molecule column in the capillary B. That call it height. Now by considering this initial volume and later volume, that is later volume is, if we call this P, the compressed molecules, if you call that pressure P into the volume is equal to the capillary area into height, that will be volume. So it is the P2 V2 is equal to the P2 V2 condition. Initial condition is PI occupying the full space into V, that is V. PI, that is P1 V1 is equal to P2 V2, like that. And now we know from hydraulics, at this point pressure here are same, and at this point PA is there at the top plus the pressure due to the liquid column. So P is equal to Pi plus gamma H, where gamma is the specific weight of the mercury. So from these two equations we can eliminate P and get an equation for Pi. That is what you have got here, AC gamma H squared over V minus H into AC. Now V is very large one. When you compare with the small capillary area, we can forget it. So now PA is obtained here by measuring height. See, all the other terms are constants given by the manufacturer. By measuring height, substitute in this equation, you have got the PA. So this is the principle of measurement. We can measure up to, this device is used up to 10 to the power of -4 tar. That is unknown vacuum pressure, we can give it and calculate the pressure there, vacuum pressure. Second method is viscous friction vacuum gauge. whenever the pressure is less than 1 torr, when Pi is less than 1 torr, that viscosity of the gas is proportional to the pressure. The viscosity eta of gas is proportional to the pressure Pi. Higher the pressure, higher will be this is viscosity, absolute viscosity of gas is proportional to Pi. Higher the pressure, higher will be the viscosity. That is what is made use of here. There is one disc rotated by a motor. This is a glass casing, it can be glass casing. Outside we have got the stator of the motor. This is motor, part of the motor. And to the inner disc, that shaft, we connect the rotor, that is inside. So when you send current here, the rotor will rotate at very high speed, maybe of the order of 12,000 RPM in one given setup. So now the distance between the two discs, one is stationary disc, another rotating disc, should be less than, suppose this is S, so S should be less than mean free path of the molecules, mean free path of the molecule. Then only the viscosity is proportional to the pressure. So it is more or less very near. And now due to this presence of molecule, there is some viscosity. Due to viscosity, the torque from the rotating disc is transmitted to the stationary disc. So due to the torque, it will tend to twist. That is, we have got a quartz fiber with its elasticity, it will tend to twist. And you have a light ray from source, and it will be reflected to a optical scale. So for optical scale is written in terms of vacuum pressure. That is, so for different pressures we can get the reading, and for each gas we have to calibrate this instrument. After calibration we can use it. And also this instrument is also used in finding this principle. The viscosity is proportional to pressure. The torque transmitted to the disc is proportional to viscosity. That principle is used in viscosity meter also. Viscosity meter. For measuring viscosity of the liquids, we find similar arrangement is there. The rotating disc there, the liquid at different temperatures, it will be kept there. Whatever torque transmitted is proportional to viscosity. That is same principle used there, but here we are using that principle for vacuum measurement. And this another one, this thermal conductivity. This Pirani gauge is based upon thermal conductivity. Thermal conductivity, that is proportional to again pressure. Thermal conductivity is proportional to pressure. That when Pi is less than, that is when Pi is less than 0.1 torr. This is the physical property what is made use of there. For that you have the resistance element middle of this casing. It may be metallic cylinder or a glass cylinder. So the filament made of tungstens, some good material, conductive material, it will be put at the middle of this case of the cylinder. So when you switch on this, when you give supply to the circuit or the bridge circuit, you will find it is being heated up. This heat will be taken to the casing by the molecule which presents. Higher number of molecules will carry a large amount of heat, proportionately larger heat. So then the temperature will come down, and then at proportional temperature it assumes a resistance. So this you have to calibrate it. So for calibration purpose, we fill this volume with the vacuum gas at say 1 torr, and the adjacent arm is a similar unit, dummy head. It is it's evacuated, completely evacuated. Similar head, but completely evacuated and sealed. So adjacent arms. You can have similar resistance, but it is easy to have the dummy head and fix it as adjacent arms. This is completely evacuated. Now fill this volume with gas with 1 torr. That means you will have enough amount of molecule to take the maximum amount of heat from the filament to the casing. Then temperature will be low, and resistance also will be low accordingly. We have learnt the resistance is proportional to temperature under resistance thermometers. So the resistance is low. Now you adjust the potentiometer so that current here is 0. Imbalance current is 0. So when at the 10 to the power or 1 tar, you will have the more or less 0 reading here, 0 reading. I is 0 through this. Now send known vacuum, you can apply known vacuum because it's a calibration process. Then when we apply vacuum that is less than 1 tar, the temperature will be increased because less number of molecule taking the heat from the filament, and then temperature will increase, the imbalance will come, and you will have some current value here. So that is for one pressure. Similarly, you can use it for different pressures, different vacuum pressures. So this is 10 to the power minus 3. 10 to the power minus 1 to 10 to the power minus 3 is the normal range for Pirani gauge. Pirani gauge is often used in conjunction with vacuum pumps. When you order a vacuum pump, that manufacturer also supply a Pirani gauge to measure the vacuum created by the vacuum pump. So this is the principle. And the range is 10 to the power minus 1 to 10 to the power minus, that is a range. It's a short range because if the vacuum falls below 10 to the power minus 3, what happens? The heat is conducted not by gas molecules but by the support. Support of the wire will carry the heat to the casing, and hence the principle is very much affected. That's why Pirani gauge work within the limited range of 10 to the power minus 1 to 10 to the power minus 3 tar. So as the vacuum is increased, the imbalance increase because resistance is keep on increasing, though current is increasing. This is the calibration curve. Later on, for the same gas, unknown pressures, unknown vacuum pressure can be found out by this. So the arrangement of the circuit is like this. So it forms one of the forearms of the Wheatstone bridge, a dummy head with adjacent arm. These are all constant resistance. If we call R1, this is R2, R3, R4. This is for initial balancing of the bridge for the calibration purpose. The last method for the measurement of vacuum is, this is we can use it for Pirani gauge. Pirani gauge range is 10 to the power minus 3, but here this one is going 10 to the power minus 10 tar. It's very high range. The principle is like this. It is a somewhat triode tube, electronic tube. It resembles electronic tube, where we have a cathode and its own circuit, heating circuit. It is a battery, and the grid circuit has its own circuit, and the cathode to anode also we have another circuit. So the anode is positively charged with reference to cathode, and grid is negatively charged. This is negatively charged with reference to cathode. These are the circuits, and this is independent. 3 independent circuits we have supply we have got. So the gas molecule or the vacuum process are allowed here, and it will occupy the space inside the tube. And when we heat this cathode element, the number of electrons will be coming out. Yeah, millions of electrons. When they hit the gas molecule, the gas molecule is made into positively charged and negatively charged ions. So the positively charged ions are attracted by this grid, which is negatively charged with reference to cathode, and there is a current flow through this grid circuit in terms of microamp. The negatively charged ion will travel with the other electrons, and it will form very small part of it, and it will attracted by anode, and it will go through this circuit, the ion current IE. But that IE will not be changed by number of hits. The racing electrons hitting the gas molecules, and that the number of molecules hit decides the current flow, that is number of positive ions decides the, that indicates the hit or the number of particles hit by the racing electrons. So that again in another terms it indicates the vacuum pressure. More and more pressure means more molecules come here, so that's why it indicates the vacuum pressure. So this reading in this grid circuit, the ammeter in the grid circuit is calibrated in terms of the vacuum pressure. When vacuum pressure falls down, then less number of molecule, less current will flow here. So that means vacuum is more. So like that, this is calibrated, and it can go up to 10 to the power minus 10 tar. It is sensitivity is up to that. The one drawback is, suppose this is a heated element cathode. Suppose we allow without knowing large amount of molecules or larger pressure, then this may be burnt. To avoid this situation, what they do, they go for it's a hot cathode. This is a hot cathode. Go for cold cathode. then to pull the electrons, you should have the high, this will be of the order of 5 kilovolt. If you have a cold cathode, then this battery will be in terms of kilovolt, then you can pull these electrons, and as it races, it hits the molecules, proportionately we have current, and accordingly we calibrate in terms of the vacuum. So that completes the methods of measurement of vacuum.